Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is 9.2, and 9.2 is Series and Convergence. All right. So first, let's define what a series is. A series is a sum of the terms of a sequence. All right. A series is the sum of the terms of a sequence. So let's recall. So a sequence was something like a sub n. A series is the summation of all those terms. And remember, those terms start at 1 and we're going all the way up to infinity using just the natural values. So in here, this is a series, the summation of all the terms of the sequence. In other words, we're saying here a sub 1 plus a sub 2 plus a sub 3, so on and so forth, all the way up until we get to infinity. All right, so that is a series. Now a way to think about this is, well, let's think of a good comparison here. A sequence, well, let's do it this way. A sequence is loosely based off of a function. All right, it's very similar to a function in general. All right, this is also true for series. So a series, so the summation from 1 to infinity of a sub n, is very similar to the integral from 1 to infinity of f of x dx. All right, so that's a good way to think about the distinction between the sequence and the series. All right, a lot of times when a student starts chapter 9 here, they get confused between the difference between what a sequence is and what a series is. A sequence is kind of like a function. A series is kind of like an integral. All right, so those are two very, very distinct things. So in here, with a sequence, we're just asking about the terms of those values, right? When you plug in 1, plug in 2, plug in 3. But over here with a series, we're asking about the sum of all those values. All right. So now, let's get a definition here. Convergent and divergent series. And a lot of the remaining of, well, a lot of chapter 9 is going to be focused into convergent and divergent series. So for the infinite series, the summation from n equals 1 to infinity of a sub n, and well, for that infinite series, the nth partial sum is s sub n, which means a sub 1 all the way up until our specified value of n. All right. If s sub n converges to some value s, then this series, hold on, let me rephrase that. That's not how I wanted to phrase that. If the sequence of f sub n, there we go. If the sequence of partial sums s sub n, remember that's the notation for sequence, converges to some value s, then the series, so the summation from n equals 1 to infinity of a sub n converges. So if we have that the sequence of partial sums converges, then the sum overall, the series, also converges. The limit s, this s, is called the sum of the series. All right. So if so the limit s is called the sum of the series. If the sequence of partial sums f sub n diverges, then the series also diverges. All right. So in here we're saying we're starting with an infinite series, right? We're going from 1 all the way to infinity. If we stop, for example, at 30, right? Let's say n is 30. Then the partial sum is just the sum of the first 30 terms. If I'm talking about the fifth partial sum, then that's really saying the sum of the first 5 terms. If I'm talking about, well, so on and so forth, right? That's just talking about the sum of the first n terms. In here, if we start looking at the sequence made by those partial sums, s sub 1, s sub 2, s sub 3, s sub 4, and if you see that that sequence converges to some value, then the series itself also converges, and it converges to that value s, that sum overall. And we like to call that limit just the sum of the series. If the sequence of partial sums diverges, then the series also diverges. All right. So let's look at an example as to what we can mean here. All right. So let's look at this series, the summation from 1 to infinity of 1 over 2 to the n. So let's look at the sequence of partial sums. So what would s of 1 be? S of 1 would be just 1/2, right? Plug in 1. So we're going from 1 all the way up to 1. Okay. And perhaps I should write it this way. It would be the summation from n equals 1 to 1 of 1 over 2 to the n, which is just 1 over 2. What would s sub 2 be? S sub 2 would be the summation from n equals 1 to 2 of 1 over 2 to the n, which would be 1/2 plus 1/4, right? 1/2 plus 1/4 because we're doing plug in 1, 1/2, plug in 2, 1/4. S sub 3, what would that be? The summation from n equals 1 to 3 of 1 over 2 to the n, which would be 1/2 plus 1/4 plus 1/8. All right. So on and so forth. All right. So in here, 1/2 plus 1/4, well, that's 3/4. 1/2 plus 1/4, that's 3/4 plus another 8. That's actually 7/8, right? You can come up with a common denominator here. I end up with 4 plus 3. Excuse me, 4 plus 2 plus 1. That's how I get that 7/8. All right. Let's do another one. Let's do S of 4. S of 4. What would that be? That would be the summation from n equals 1 to 4. And perhaps I should space these out a little bit better. I'll do S of 4 on the side over here. S of 4. That would be the summation from 1 to 4 of 1 over 2 to the n, which would be 1/2 plus 1/4 plus 1/8 plus 1/16, which ends up being 15/16. S of 5. The summation from 1 to 5 of 1 over 2 to the n, which would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, which would give us 31 over 32. 16 plus 8 plus 4 plus 2 plus 1. All right, so these are the partial sums. Now let's see what would s sub n go to. All right, so what's this sequence really? Let's look at our terms. 1/2, 3/4, 7/8, 5/16, 1/32. Excuse me, 31/32. If you look at the denominators, all the denominators are powers of 2. Okay, that's exciting. But more importantly here, what we're really trying to figure out is how can we relate the numerator and the denominator? Well, between the numerator and the denominator, the numerator is just 1 less than the denominator, right? 3 is 1 less than 4, 7 is 1 less than 8, 15 is 1 less than 16, 31 is 1 less than 32. So we just said that the denominator was powers of 2, and the numerator was just 1 less than that. So in general, this series of the summation from 1 to infinity of 1 over 2 to the n can be written as this partial sum of 2 to the n minus 1 over 2 to the n, all right? And in here, if I take the limit here of this sequence s sub n, all right, and again, this s sub n represents the sequence of partial sums. So let's do the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. All right. Well, how would we do this? Well, if I plug in infinity, I go to infinity over infinity, right? 2 to the infinity is infinity, 2 to the infinity is infinity. But what we can do here is we can multiply by 1. If I multiply by 1 over 2 to the n over 1 over 2 to the n, well, what does that give me? That gives me the limit as n goes to infinity of 1 minus 1 over 2 to the n over 1. And as n goes to infinity, this piece right here goes to 0. So overall, this entire thing goes to 1. So what does that tell us? That tells us that the limit of the partial sums, of the sequence of partial sums, went to 1. So what that implies now is that the original series from 1 to infinity of 1 over 2 to the n, it goes to 1. It converges to 1. All right? So we can say it converges and its sum is 1. All right, next example. So that was A. B. Let's say that we had the summation from n equals 1 to infinity of 1 over n minus 1 over n plus 1, right? So let's get our partial sums here. So if I start with s sub 1, what would s sub 1? That would be the sum from 1 to 1 of 1 over n minus 1 over n plus 1, which would be 1 minus 1 half, which is just 1 half. Okay. S sub 2, that would be the summation from 1 to 2 of 1 over n minus 1 over n plus 1, which would be 1 minus 1 half, right? Let's plug it in 1, plus plug in 2, 1 half minus 1/3. Notice here that the negative, so parentheses in general are not doing anything, but this negative 1 half plus 1 half cancels each other out, and then I've got 1 minus 1/3, which is 2/3. S sub 3, the summation from n equals 1 to 3 of 1 over n minus 1 over n plus 1, which would be 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus 1/4, right? I'm plugging in 1, 2, and 3 into both of these. And in there, what do we see? We see that 1 half and 1 half cancel out, negative 1/3 and positive 1/3 cancel out. So overall, we end up with 1 minus 1/4, which is 3/4. I'll do another one more. We're going from 1 to 3 of 1 over n minus, from 1 to 4 of 1 over n minus 1 over n plus 1. So what does that give us? 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5. And what would that give us? Well, let's see. Again, we end up with these cancel out, these cancel out, these cancel out. So it's just 1 minus 1/5. And 1 minus 1/5 is 4/5. All right, so now we've got a pretty good pattern going here. So let's see what is it that you see is going on here. All right. If you'll notice, well, maybe I'll do just one more to make my point a little bit more clear. We have a lot of stuff canceling out, right? So let me go ahead and finish it. So let's plug in 1, plugging in 2 is 1 half minus 1/3 Plugging in 3 is 1/3 minus 1/4, 1/4 minus 1/5, and then 1/5 minus 1/6. And let's look at what the pattern here is. Every single term in the middle cancels out except for the first and the last. And that's exactly what happened in the previous steps, right? I mean, in the first partial sum, there were no steps in the middle, right? There was no middle terms. But the first and the last one still remain. The first and the last one remain. The first and the last one remain. First and last. First and last. So in here, what does that give me? So 1 minus 1/6 is 5/6. So I think at that point you can start to see really what this partial sequence is. Excuse me, what the sequence of partial sums is. All right. Let's look at the numerators. 1, 2, 3, 4, 5. So the numerator is just n, right? Because when n was 1, numerator 1, 2, 2, 3, 3, 4, 4, 5, 5. And the denominators, they're just one bigger than the numerator, right? Plus 1, plus 1, plus 1, plus 1, plus 1. So the denominator is n plus 1. So now, let's see what this limit goes to. If I take the limit as n goes to infinity, right? And well, let me actually write something here, because I want to make explicit something I mentioned. First and last term are left. So the first term, 1, minus the last term, 1/6. The last term, if I'm going all the way up to n, is going to be n plus 1. This, come up with a common denominator, n plus 1, n plus 1 minus 1, right? This is how that would end up being split. And now we get exactly what I had said before of n over n plus 1. All right, so whether you look at it through looking at what the sequence of partial sums is given out and write it that way directly, or if you realize that it's just the first term and the very last term, we end up with the same exact solution there for our partial sum. Now, in there, let's take the limit. If I take the limit as n goes to infinity of our partial sums, and I'm going to go off of this definition here. So the limit as n goes to infinity of 1 minus 1 over n plus 1. Well, that 1 over n plus 1 as n goes to infinity, that goes to 0. So overall, I end up with 1. All right, so in this case, I also had that the sum went to 1. So what we're saying here is that this summation, the series from n equals 1 to infinity of 1 over n plus 1 over n plus minus 1 over n plus 1, that's going to go to 1. So it converges again. It converges and it converges to the sum of 1. All right. Now, this series right here, this has a very specific kind of pattern. All right. And I want you to again think about what I said before, specifically here. First term and the last term. So this sequence, when I expand it out, this series, when I expand out this series, I'm left with just the first term and the last term, essentially compressing the entire sum to just be one term at the very beginning and the one term at the very end. So we're compressing that entire sum. This is called a telescoping series. So, telescoping series. And why would it be called a telescoping series? Well, think about a telescope. What does a telescope normally look like, right? We have, let's see how awesome my drawing skills are right now. This is a telescope, right? If you think about what a telescope normally looks like. And this telescope can be compressed to just be something like this, right? With a whole bunch of like little lines there for compression. So we can compress the telescope to get rid of all the middle stuff and just deal with the beginning and the end of it that way. That's why this is called a telescoping series, all right? Because you can compress it to be kind of like similarly to a telescope. Now, let's look at an example. So let's say that we had this series from 1 to infinity of 2 over 4n squared minus 1. All right. So in here, 2 over 4n squared minus 1. Well, this looks different than the last one, right? Because in the last one, we had two fractions. We were subtracting these two fractions. And it's that subtraction of two fractions that we were adding up all of these subtractions. That's what allowed all the middle terms to cancel out. But in here, I don't have two fractions. So why am I putting this with telescoping series? Well, it turns out that we can rewrite this fraction. All right? Let's see how we can rewrite this fraction. So I have 2 over 4n squared minus 1. This is the same thing as saying 2 over 2n plus 1 times 2n minus 1. And I'm trying to write this one fraction as multiple fractions. This should remind you of something that we discussed early on in this course. This should remind you of partial fractions. In fact, this is what we need to do right now. We need to do partial fractions so that we can rewrite this series. So let's do partial fractions. So what we're saying here is that this needs to look like a over 2n plus 1 plus b over 2n minus 1. And what does that tell us? Now, if I multiply everything by the common denominator, that tells me that 2 is equal to a times 2n minus 1 plus b times 2n plus 1. And now that I have that, if n is equal to, let's start with 1/2, well, what happens? If n is equal to 1/2, 2 times 1/2 is 1. 1 minus 1, oh, that cancels out. So the right side is just 2, and the left side is just 2, and the right side, this piece canceled out, so I still have b times, plug in 1/2. 2 times 1/2, 1. 1 plus 1 is 2, so that b is equal to 1. Cool. What if n were equal to negative 1/2? Well, when n is equal to negative 1/2, the left side is still just 2, but the right side, plug in negative 1/2. 2 times negative 1/2 is negative 1. Negative 1 plus 1 goes away, so this part completely goes away, and we're just left with a times, well, plug in negative 1/2. 2 times negative 1/2 is negative 1. Negative 1 minus 1 is negative 2. So that a is equal to negative 1. Right? Now that I've got that, I can go ahead and rewrite my fraction. So that tells me now that we're going to get negative 1 over 2n plus 1 plus 1 over 2n minus 1, right? Negative 1 and 1. Now this I can rewrite, right? We know that when we have a sum, we can just change the order. So I can rewrite this as 1 over 2n minus 1 plus the negative, well, plus and negative is minus. So there we go. 1 over 2n minus 1 minus 1 over 2n plus 1. So at that point, what we've got is that our sum from 1 to infinity is equivalent to saying 1 over 2n minus 1 minus 1 over 2n plus 1. And let's see what happens here. Let's start plugging in some values, all right? Let's start plugging in some values of here. In other words, what we're trying to do here is figure out the partial sum s sub n. All right, I'm going to just go up to n. So plug in 1. 2 times 1 is 2 minus 1 is 1. So I have 1 over 1 is 1. Minus, plug in 1. 2 times 2 is 2 plus 1 is 3. So I have minus 1/3. Plus, plug in 2. 2 times 2 is 4 minus 1 is 3. So I get 1/3. Minus 1 over, we're plugging 2. 2 times 2 is 4 plus 1 is 5. Plug in, so that was plugging in 1, 2. Let's plug in 3. 2 times 3 is 6 minus 1 is 5. 2 times 3 is 6 plus 1 is 7. So on and so forth, right? Until we get to 1 over n, excuse me, until we get to 1 over 2n minus 1 minus 1 over 2n plus 1. And let's look at the pattern here. In here, negative 1/3 plus 1/3 cancels out. Negative 1/5 plus 1/5 cancels out. Negative 1/7 is going to cancel out over here in the very next term. This last term over here is going to cancel out with this first term over here. So what we can really say here is that S sub n is just the first term minus the last term. And that's what makes this a telescoping series. And now, if I take the limit as n goes to infinity of that, the limit as n goes to infinity of 1 minus 1 over 2n plus 1, well, that piece, that fraction, goes to 0. So I have 1 minus 0, which is 1. So once again here, we end up with a series that converges to 1. Its sum is 1. All right. Now, that was geometric series. Excuse me, that was telescoping series. Let's move on to geometric series. So, and before we talk about geometric series, first let's talk about a geometric sequence. A geometric sequence is of this form. So let's do it this way. A geometric sequence is, we start with some term, and then we multiply it by r, and then we multiply it by r again, and then we multiply it by r again, and then we multiply it by r again, to the fourth. So on and so forth. We multiply it by r again. All right, that's a geometric sequence. It has a common ratio. So another way to do this is a geometric sequence has a common ratio between consecutive terms. In other words, if I take this one and this one and I divide them, AR divided by A, I end up with just R. If I take this one and this one and divide them, AR squared over AR is just R. AR cubed over AR squared, R. AR to the fourth over AR to the third, R. So on and so forth. All right, so there we have a common ratio. Now, that's a geometric sequence. Now let's talk about a geometric series. Well, a geometric series is just a series. I'll talk about the bounds in a second. A geometric series is a series of a geometric sequence. All right, where a is just whatever value we want to start with. All right, so in here we're saying this is a plus a to the ar plus ar squared plus ar cubed, so on and so forth. Now, the one thing about geometric series is that they start at 0. All right. Prior to this, we had our geometric series start at 1. Adding one extra term here just for the geometric series does not really affect the way that we thought about anything else that we said there. Now, that's what a geometric series is. So, how do we tell if something like this converges or diverges? Well, let's see. A geometric series with ratio r diverges when the absolute value of r is greater than or equal to 1. If the absolute value of r is strictly between 0 and 1, in other words, it is a fraction between 0 and 1. It's not 0, it's not 1, but it's a fraction somewhere in between. So if the common ratio is between there, then the series converges to the following. So it converges, and it converges to, well, let's write it this way. The summation from n equals 0 to infinity of ar to the n. That's going to be the same as saying a over 1 minus r. And again, here assuming that our r is strictly between 0 and 1. It cannot be 1 because if it were 1, 1 minus 1 is 0, and then we're dividing by 0, we don't like that. But again, here with the geometric series, we must have that we're starting at 0, all right? So now, let's do some examples with this. And again, the idea here is, does this converge or diverge? So let's say that I had the sum from 0 to infinity of 9 over 3 to the n. All right. So in here, what we can say is, well, this is the same thing as saying the sum from n equals 0 to infinity of 9 times 1/3 to the n. In here, our r is 1/3. Our a is 9. So because r is 1/3, we know that this is going to converge, right? 1/3 is between 0 and 1, right? Even the absolute value of that is between 0 and 1. So what this tells us now is that we're going to get that series is going to be equal to a over 1 minus r. Our a is 9. So 9 over 1 minus 1/3. 1 minus 1/3 is 2/3. 9 divided by 2/3, well, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And here these reduce, giving me 6. So, that's wrong. I said multiply by the reciprocal of that fraction, and I didn't take the reciprocal. Multiply by the reciprocal. The reciprocal of 2/3 is 3/2. There we go, giving us 27/2. Okay, way better. So in there, our summation, our series there, our geometric series, adds up to 27/2. All right, and that's a convergent series. Let's look at another one. The summation from n equals 0 to infinity of 5/4 to the n. All right. Now in here, what's a? Well, a is just 1, right? It's an invisible 1 here. So a is 1. And r is 5/4. 5/4 is bigger than 1. So right away, I can say that this is divergent because the common ratio, that r, was bigger than 1. So we're done. We don't even have to do anything else. Let's do another one. Let's say that I had this. Let's say we have, I don't know, 4 times negative 1/3 to the n. Let's do something different. Instead of negative 1/3, let's use negative 2/5. All right, way different. Everything changes now. So, okay. So now, in here, what's our common ratio? Well, first let's figure out what a is. A is 4. Cool. Our common ratio is negative 2/5. Good. Negative 2/5. Well, if I take the absolute value of that, the absolute value of negative 2/5, that's strictly between 0 and 1, which is good. So we know it is convergent. Except for one thing here. I mean, it is convergent, but here's something that we've overlooked. Notice here that I made a specific comment there about that it has to start at 0. This one, I have it starting at 1. So we can't really just go ahead and do and apply all the shortcuts yet, because this is starting at 1. I need it to start at 0. So how do I start at 0? Well, what I'm going to do here is I'm going to add one more term to this entire sequence, to this entire series somehow. And well, how am I going to do that? Well, what I'm going to do here is I'm going to add 0. So how am I going to add 0 here? So let's see. This is going to say, well, I'm going to add 4 minus 4. All right. And well, let's do it this way actually. Negative 4 plus 4. And why am I choosing that? Why am I choosing that? if I want to add the term of 0, well, what will happen if I plug in 0? Negative 2/5 to the 0 is just 1. So I'm left with 4. So I'm subtracting and adding 4, right? Because those two right there are just 0. And then I still have the rest of my summation. And now, from there, well, these, if I throw this into here, now I can say that I end up with negative 4 plus the summation from n equals 0 to infinity of 4 times negative 2/5 to the n. All right. Now we can go ahead and apply all these things that we have over here, right? So because again, now we've got our series starting at 0. And again, notice that I took the positive 4. Why did I take the positive 4? Because if I were to plug in 0, negative 2/5 to the 0 is 1. 4 times 1 is 4. So essentially, I added the term that still works with the overall pattern. I would not have been able to put the negative 4 into there and keep the positive 4 on the outside because that negative 4 would not follow the pattern overall when n equals 0. And okay, so now what do we get? This negative 4 is still on the outside, plus inside here. What can we do? This, we just said it goes to a over 1 minus r. So a is 4 over 1 minus r, negative 2/5. So what do I get? So I still have this negative 4 on the outside. 1 minus negative 2/5, that's 1 plus 2/5, which is 7/5. So I have 4 over 7/5. Dividing by a fraction is multiplying by the reciprocal, so negative 4 plus 4 times 5/7. Coming up with a common denominator, I have negative 28/7 plus 27. So overall, I end up with negative 8/7. All right. So that's what this series all adds up to, negative 8/7. And again, that's because we needed to add that extra term in there so that we can actually apply the rule for geometric series. All right, now let's look at an application of geometric series. All right. So I guess I'm at letter G, I believe. Yeah, G. Use geometric series to write 0.7 repeating as a fraction. All right, so let's look at this. If I have 0.777777, so on forever, right? Because that's 0.7 repeating, that's what that looks like. Well, what does this really look like? Well, this is really just saying 0.7 plus 0.07 plus 0.007, so on and so forth, right? I'm just splitting it up into each of those sevens separately. All right, let's not deal with decimals. Let's deal with fractions. 0.7, that's 7/10. 0.007, excuse me, 0.07 is 7/100. 0.007, that's 7/1000, so on and so forth, right? And at that point, let's see. If I factor out a 7/10, what am I left with? So 7/10 times 1 plus 7 divided by 7 is just 1. 100 divided by 10 is 10. And by similar reasoning, I end up with 1 over 100 and 1 over 1,000 and 1 over 10,000. Look at this. This right here, this is a geometric series. How do I know that it's geometric? Well, going from one term to the next, all I'm doing is multiplying by 1 over 10, right? 1 plus, so I multiply 1 by 1 over 10, 1 over 10. Multiply by 1 over 10, 1 over 100. Multiply by 1 over 10, 1 over 1,000. In other words, what I'm saying here is that what we really get is 7/10 times 1 plus 1/10 plus 1/10 squared plus 1/10 to the third plus 1/10 to the fourth, so on and so forth. So now that I have it written this way, I know what my common ratio is. My common ratio is 1/10. My A is this value all the way over here that I factored out. All right, so what we really have here is we've got the summation from n equals 0 to infinity, right? And it starts at 0 because in here this is technically 1/10 to the 0, right? Of 7/10 times 1/10 to the n, right? And now we can go ahead and figure out what this is supposed to go to. A, which is 7/10 over 1 minus r. So my 1 minus 1/10. So I have 7/10 divided by 9/10, right? 1 minus 1/10 is 9/10, which gives me 7/10 times 10/9. These tenths cancel out, so I end up with 7/9. All right. So there you go. I ended up with 7/9. So that's one example there. Let's do a slightly different version of this. So that was G. H. So again, semi-stack instructions, but now we're gonna write 0.81 as a fraction. All right. And now, how is this different? Well, the difference is that now we're repeating two values versus just repeating one value, right? So in here, what is this really saying? This is really saying 0.8181818181 forever, right? What is that really? So that's if I apply the same exact thing, the same pattern that I did before, that's 0.81 plus 0.0081 plus 0.123481 plus 0.12345681, so on and so forth, right? Now, let's see. Let's rewrite all those as fractions because decimals are awful. 81 over 100 plus, right? It's 100 because it's two decimal places. 81 over 1, 2, 3, 4. So 1, 2, 3, 4 zeros. So 10,000 plus 1, 2, 3, 4, 5, 6. So 81 over 1, 2, 3, 4, 5, 6 zeros. All right. So on and so forth, right? And now if I factor out an 81 over 100, what am I left with? Well, this piece is just 1 plus 81. Factor that out, so I just have 1. On the bottom, I have 10,000. I factored out 100, so 10,000 divided by 100, so cancel out 2 zeros, so I end up with 100. Similarly, cancel out 2 zeros. I had 6 zeros, so 1, 2, 3, 4. I put the comma in the wrong place, so it's 10,000. And the next one, well, how many zeros do you think it'll be? You guessed it, it is 6 zeros. 1, 2, 3, 4, 5, 6. So on and so forth. But again, the idea here is that this is a geometric series now, in parentheses, right? Where our common ratio is 1 over 100. So I have 1 plus 1 over 100 plus 1 over 100 squared plus 1 over 100 cubed, so on and so forth. Which tells me now that I can rewrite this as the summation from n equals 0 to infinity of 81 over 100 times 1 over 100 to the n. And now in here, we already know that r is equal to 1 over 100, which is less than 1 and bigger than 0. And our a is equal to 81 over 100. So what is this going to be? Well, now what this tells us now is that we have a over 1 minus r. So a was 81 over 100. 1 minus r. R was 1 over 100. 1 minus 1 over 100 is 99 over 100. And at that point, dividing by a fraction is multiplying by the reciprocal. The reciprocal of 99 over 100 is 100 over 99. The hundreds cancel out, so I end up with 81 over 99. They're both divisible by 9. 81 divided by 9 is 9. 99 divided by 9 is 11. So we have 9/11, right? So that's a way to work with, or that's a way to rewrite repeating decimals as fractions, all right, using geometric series. All right, so now some properties of infinite series. Properties of infinite series. Okay. Um, and I'll just go ahead and write the properties. If I have this summation or the series of c times some sequence a sub n, you know what? I need to preface this with a little bit. Let's say that the series of a sub n, it adds up to a. The series of b sub n, it adds up to b. And let's let c be a real number. And a and b are also real numbers, all right? But now, all right, so now let's go ahead and write the properties. If I have the summation of c times a sub n, and it should be lowercase a, that's going to be just c times a. If I have the summation of, or the series of a sub n plus or minus b sub n, that's going to be a plus or minus b, right? So that's essentially just, I mean, that's true overall for any summation, but in here we're also saying it for infinite series, that they're going all the way up to infinity. That just allows us to be able to manipulate things, all right? That property. But now, let's talk about this theorem, which is a very important theorem. The limit of the nth term of a convergent series. And this is what it says. It says if the series of a sub n converges, then the limit as n goes to infinity of a sub n is equal to 0. If the series converges, then the limit goes to 0. I'm going to make a very important note here. This does not mean if the limit goes to 0, then the series converges. All right? It does not mean that. In fact, it is wrong to think that. All right? It is possible for the limit for a sequence to go to 0 and the series to diverge. All right? This is false. This sometimes happens, but it's also a lot of times false. So not necessarily true. What is true is that if it converges, then its limit goes to 0. Now, well, how is that useful? We're trying to figure out whether or not a series converges or diverges. And as written, this theorem, well, we first must know if the series converges to figure out the limit of the sequence. Well, we can rewrite that theorem as follows. And this theorem is called the nth term test for divergence. And this is what the theorem says. It says if the limit as n goes to infinity of a sequence does not go to 0, then the series of a sub n diverges. All right. So if the limit does not go to 0, then the series, if the limit of the sequence, excuse me, if the limit of the sequence does not go to 0, then the series of that sequence does not converge. In other words, it diverges. All right. That is equivalent to this statement. All right. If the series of a sequence converges, then the limit of that sequence goes to 0. All right. That's equivalent to saying this. Now, this one over here is way more helpful, this version. Why? Because now we can talk about things happening with the sequence so that we can make conclusions about the series. All right. So, for example, what letter am I at? I think I, maybe. Yeah, I. So I. Let's say that I have the series from, well, I should be going from, I could go from 0. From 0 to infinity here. Well, if I take the limit as n goes to infinity of 3 to the n, that's infinity. Is infinity equal to 0? No. So it did not equal 0. Does not equal 0. So that tells me that that series diverges. Let's look at another one. If I had the series of from n equals 0 to infinity of, let's say I had n factorial over 6n factorial plus 7. Well, if I multiply this by, well, no, let's not do that yet. We want to figure out the limit here. So let's take the limit as n goes to infinity of n factorial over 6n factorial plus 7. And what I'm going to do here is I'm going to multiply by 1, right? 1 over n factorial over 1 over n factorial. That fraction is just 1. And when we do that, we get the limit as n goes to infinity of 1 over 6 plus 7 over n factorial. And 7 over n factorial as n goes to infinity, that goes to 0. So I get 1/6, right? And now that I have 1/6, 1/6 is not equal to 0. So it tells me that, well, since it's not 0, then that original series diverges, right? Because it's not 0. Okay. Let's look at the summation from n equals 1 to infinity of 1 over n. Right? So let's take the limit. The limit as n goes to infinity of 1 over n equals 0. So what does that tell us? It tells us nothing. It tells us absolutely nothing. Because let's think about what I wrote over here in this note. If the limit goes to 0, then that converges. That is not true. That is not necessarily true. That's not what this theorem is saying. All right. The fact that it goes to 0 doesn't tell us anything. The fact that it doesn't go to 0 from the nth term test, so not going to 0 tells us divergent, but going to 0, it tells us nothing. All right, this tells us nothing. So the fact that this limit of 1 over n goes to 0, well, nth term is inconclusive. The nth term test is inconclusive, or we can say it does not apply. All right, because the nth term test was for when things were not going to 0, not when they were going to 0. All right. So in there, you have to keep that in mind. In fact, I mean, you'll see in a different lecture going forward. We'll see what this actual series goes to. All right. And I will tell you right now, it does not converge. It does not converge. It diverges actually. But we'll see why um, in a different lecture. All right. That is the end of 9.2.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.